then I'm gonna minimize the video so I don't bother me. Okay, perfect. So let me know when you want me to start. I can wait a couple of minutes.
Yeah. All right, I will.
Okay, ready?
Hi, Joan. Yeah, we can start now.
Perfect. Okay, so hello everyone. So welcome again. Today I'm going to be following up from where Peter left it 2 days ago, and I'm going to be telling you a bit about grids. So just to recap from past lecture, and also tell you a little bit the objectives for today. So Peter explained to you about how to instantiate the blueprint on different domains, in particular sets and graphs. And I believe that he was really, he leveraged quite a lot the spatial structure of the problem. So he really spent a lot of time describing this model from the spatial domain. And today we are going to focusing on a let's say simpler domain, which is the grid. As you will see, we are going to complement this spatial view with other views that in particular involve the spectrum and also the multiscale structure. So today we have quite a bit of things to talk about, but broadly the lecture is going to be divided into 3 blocks. First, we are going to be getting familiarized ourselves with the translation group and like the natural tool to understand translation group, which is the Fourier transform. And then we are going to see a little bit we are also going to discover some of the limitations of this view and how to address these limitations by developing and studying multiscale representations, in particular wavelet transforms. And from these 2 objects, we are going to culminate by arriving quite gently to the convolutional neural network. Okay. And as usual, please interrupt me if there's any question, or I'm going to be, of course, be available offline on Campus Wire for any questions you might have during the lecture. So let's start from the translation group. So grids, I guess by now everyone is familiar. Everyone is familiar with what we mean by a grid. So grids can come in different flavors. One can have it in 1 dimension. For example, here is like think about like a line that is discretized into different coordinates, different points. So we can have it in 2 dimensions. And so the first, let's say, very immediate question is, what are the associated transformations of this grid, right? What is the structure that this domain allows us to exploit? And as you are also familiar, as you know, the natural operation that lives very naturally in a grid is a translation. Let's first focus on how one could move a single point in the domain, right? So I have a point here on the left, so I can keep moving it. Of course, there's a little problem here, right? Is that what do we do in the boundary, right? We cannot keep moving it to the right. And so a natural thing to do in these conditions is to invent ourselves that there's a periodic boundary condition. And this is really, one can call it a mathematical convenience, but as you can see, it pays off a lot, right? It pays off big time. Because now that we have this periodic boundary condition, we can of course take this point that we had on the boundary and put it back again. And now we have thanks to this boundary condition, we can define a bijection, which is simply just taking a point and moving it to the right-hand side or to the direction that you prefer. And then we just need to take these operations in the right modular arithmetic, right? So we just need to take operations modulo D. And so this comes with a very simple, this has a lot of benefits, has very simple algebraic structure in the sense that if I have a transformation that is, I'm moving things towards the right, the corresponding inverse transformation, the inverse bijection, is simply just inverting the arithmetic operation that you see here, right? So instead of adding 1, here I subtract 1 here. And of course, if I want to compose this transformation and move things not just by 1 unit, but by k units, as here, right? So I compose this transformation k times. I just have the equivalent operation in the arithmetic group. So here we are just rediscovering the fact that the algebraic structure of this group of transformations is following, it's precisely the structure of doing arithmetic modulo D, right? This is called the cyclic group. Okay, and grids come with, of course, different flavors, right? So here we illustrated things by just using the discrete grid in 1D, but these grids can come in different flavors. As I said, one can have grids in different dimensions. The thing that is relevant for machine learning and engineering and science mostly concerns grids of dimension S here, where S is either 1, 2, or 3, right? S equals 1. Corresponds to time series, and I think Peter is going to also tell you a lot about how to process things in 1D. Is S equal 2 corresponds to images, and S equals 3 might correspond to video, for example, video sequences. Okay. So when I have a S-dimensional grid, the associated group of transformations is just like copies, Cartesian copies of the group. So here we have a translation structure that is different copies of this cyclic group. And another very natural flavor of grids is when instead of discretizing the domain, I keep it continuous. And here the object that emerges is a torus. Why is it a torus? Because you have to imagine a square, like a square where I have stitched, I created these boundary conditions. So if you take a square, like a square sheet of paper, and you try to connect the top and the bottom, and then the left and the right, you end up with a donut, right? And this is the torus. And so here, again, the symmetry structure is very natural. It's just 2 copies of S1. S1 is the circle. So here there's an interesting observation that in this case, if one looks at the group of transformations and just looks at the set structure, it coincides exactly with the domain, right? So if I think, for example, like the set of, if I create this boundary condition, I can always associate a transformation shifting an image by k pixel, by a certain amount of pixels. I can associate this with transformation basically with a coordinate in the domain, right? So I have a bijection. This is not the case in general. And Taco is going to give you, I believe, some examples where this is no longer true in more general problems. But the grid has this very nice very nice feature. Okay, so we have described transformations of the domain, and remember that in our business, we are interested in how these transformations act on signals that are defined in the domain, right? Remember that we call this kind of a lifting, right? So we lift the transformation in the domain to a linear transformation on signals on the domain. Okay, this is the relevant formula, and you can see, I mean, this is just a very simple illustration that shows that if I have a certain transformation in the domain, it's acting on signals by, as you could imagine, just the thing that you would expect, that is just moving things around. So because we are now dealing with linear transformations, a very natural question, right, is that again, if we stick with a simple example, which is a 1D grid that is discretized, I can identify the signals on that domain as just vectors in the dimensions, right? Because I just have a discrete domain, so I can just have 1 degree of freedom per coordinate. So I have a finite dimensional vector. And so if I have if these transformations are linear, a linear transformation on a finite dimensional space is a matrix. So how can we now understand these transformations in matrix form, right? So how can we associate to every little g here in the group a corresponding matrix? Okay. So the answer is this little guy here that we call this shift operator, right? So this matrix, sorry about maybe the formatting that is not ideal. It looks like a matrix that has lots of zeros and a few ones. So the ones are just above the diagonal, right? So I have the thing that is just above the diagonal. Above it's all ones, and I have one little one here in the top, in the bottom left corner. Okay, so this is a matrix that is a d by d, and as I present you a fact, is that for every element in this cyclic translation group, I claim that the action of this translation and signal can be always written as a power of this shift operator for some integer k. And this I will lead you as an exercise to try to verify this fact. But interesting consequence that is also something that I would like you to leave as an exercise is that to use this fact, the fact that I can represent now, so you can view this matrix here as the matrix that generates any element of the group, right? So every element of the group I can see it as a power of a single matrix. So how can I use this fact to prove that in that case this group is commutative, right? Or in other words, it's also called abelian, right? So it's a group that is commutative. So if I compose two elements, G and H, the order doesn't matter. Okay. And just as a remark, observe that this matrix is not so strange matrix, right? Because if you remember the picture I had you before, the kind of the illustration of this grid with boundary condition, if one looks about if one thinks about this as a graph and puts a directed structure, so let's put an arrow, right? In every one of these lines, you put an arrow, and you consider the adjacency matrix of that graph. That's precisely that's precisely the matrix S. And this is not completely unrelated to some of the properties that we are going to see later. Okay. So remember when we constructed this geometric deep learning blueprint, that the interesting aspect of the blueprint is the fact that it's sufficient to understand very well the local linear invariant and equivariant structure, right? So in other words, if we can characterize and describe perfectly the linear invariant and equivariant, then we can combine them together into a very powerful representation. Okay, so that's what we're going to do now. We're going to try to characterize completely the linear equivariant and invariant structure of the translation group. And again, I'm sticking always with my favorite example, which is the 1D case with a discrete. Okay, so let's start with the linear invariance. So a linear invariant, as I said, is a linear function from d dimensions to r that is satisfy the property that if I compose like this operator is invariant, right? So if I transform x with any element of the group, I want to get exactly the same. So how do you characterize a linear function over a d-dimensional space, right? So there's a very natural representation of this function. I cannot see the people. I guess it's because of me, but I'm hoping that. Okay, let me just see if there's some questions in the chat. Okay, well, otherwise I will continue. Okay, I'm just asking questions aloud. Please feel free to interrupt and answer the questions if you want. Okay, so this function indeed has a representation as a dot product, right? That's precisely the way to describe linear functions in the infinite dimension. Okay, so this function is the dot product of x with v for some vector v. Okay, and so now we just write down the conditions that we want, right? So what is the property of this vector v? is that this vector v, right, it's such that this map, as I said, is equivariant. Is invariant, right? So by definition, the dot product on x and v has to be the same as the dot product between g times x and v. And now if we apply the property that we saw before, namely that this group action can always be written as the sum power of the shift operator, and just putting the shift operator back with the adjoint, what we see is a very suggestive and simple formula that says that this v, right, has to satisfy that v equals to s times v. And again, I leave you as an exercise to prove that, right? I almost gave you the whole answer, right? So from how can you go from this line to this line? I leave you as an exercise. And now I also ask you to, once you have this property here, you can see that this is actually an eigenvector, an eigenvalue problem, right? So here what we are characterizing V as the eigenvector of S with eigenvalue 1. So I ask you to also prove that in that case, the solution has to be that V is the all-one vector. And as a hint, the natural tool to use that is a very famous, powerful result from linear algebra, which is called the Perron-Frobenius theorem. Again, please don't hesitate to write on Campus Wire if you have any questions about this. Okay, so this is for the invariant. Now let's go for equivariants. Okay, so equivariants, again, keeping the same setup. So now we are looking for linear operators. That now in that case, they are matrices, right? So they map RD to RD, that they commute with the action of translations. And again, using the representation as a shift matrix, right? So this has to be this operator is the matrix it's a matrix vector product for some unknown matrix. And so the condition here, using again the fact that the translation can be expressed as some power of a shift, we end up again by basically the same logic as before, that these matrices C are such that they have to commute with the shift. Okay, and again, I ask you to try to go from that point to that point. It's almost direct. So how can we characterize these matrices? Okay, so how can we understand the matrices that satisfy this equation? All right. So to do that, we are naturally arriving at the doors of Fourier. So if we look at the adjoint of S, right? So like in that case, because the matrix is real, just the transpose, we can see that the transpose of S is just shifting the domain on the opposite direction as S. Therefore, because of the group structure, we know that if we compose S transpose with S, we get exactly the same thing as S transpose, which is just identity, right? If we move first to the left and then to the right, and then we do the opposite because of the commutative property of the group, we get to the same place where we started. This in linear algebra terms, it means that this matrix S is normal. It's called a normal matrix, right? It's a matrix that satisfies this condition here, which means that I can diagonalize it, right? It's a matrix that admits a family of eigenvectors and eigenvalues by looking at the complex basis. Okay, so that's what we are going to do, right? We're going to try to understand what is the eigenstructure of the shift operator. So let's go straight to the chase. Let's cut to the chase. So let's consider this vector, right? For every k is a natural number between 1 and d, or between 0 and d, and between 0 and d minus 1, if you want, and that is given by this family of complex exponentials. Okay, so it's a vector. It's a complex vector, right? It's a d-dimensional complex vector, and if you want to illustrate let's say the real part and the imaginary part of this vector as I change k, I can go from k very small that looks like this little very smooth wave. As k increases, you get waves that oscillate more and more. Okay, so k here is associated with what we call a frequency of a wave. So there's this very simple property that it's immediate to verify, that if I do the dot product between one of these guys here and one of the rows of the shift operator, you can verify that you get at the output, you get the coordinate of the original vector, right, at the coordinate j, times a coefficient. So in other words, what we have just seen is that these guys here, these vectors, these waves, are eigenvectors of the shift operator with eigenvalue that is associated with this coordinate here, right? That the key point here is that this thing does not depend on J, right? So it's so you get this equation. And in fact, it's easy to verify that these are all the eigenvectors of S, right? So all of the eigenvectors must have this form. And again, this is left as an exercise for you. Okay, so these vectors should be no surprise, and I'm hoping that you are familiar, you have encountered these guys in the past. So these vectors together define a Fourier transform, right? So if we stack all the vectors together into a matrix, if you want, or like a linear transformation, this defines a transform of X, right? So if X is a signal over a grid, and I apply this matrix, I get a new signal, a new vector, which is in general complex, and this is called the Fourier transform of X. It's the discrete Fourier transform. Okay, and so this is the definition that you get here. So this transformation is almost, I would say it's almost magic, right? In the sense that it has very powerful, rich properties. It defines an isometry. So in other words, the dot product structure is preserved, right? So if we measure similarity between two vectors, X and Y, we can define the similarity both in the spatial domain, the original domain, and the spectral domain. It comes with an inverse transform, right? So if you think about this as some matrix multiplication, this matrix V admits an inverse. In fact, it's just its own conjugate transpose. Okay, like the inverse Fourier transform can be computed very, very naturally. Here I didn't write it here, but in practice, the reason also why it's so popular is that in practice, we do not implement it with a matrix vector product. We implement it with fast algorithms, which is called the fast Fourier transform, which is like a massively important algorithm. And this definition that you see here that works for the discrete case, it admits natural generalizations to all the things that you can imagine, right? So the domain that is continuous admits a Fourier transform. Even if there's no boundary, there's a Fourier transform. If multiple dimensions, there's a Fourier transform, and beyond, right? So even if the signal is not even in L2, even if it doesn't have a finite energy, one can still define a Fourier transform. And it's no surprise that the Fourier transform is really instrumental in many, many, many areas of math and engineering, and even like now machine learning. Okay, signal processing, partial differential equation, mathematical physics, even in number theory, graph theory, many, many places. So you might be wondering, what does it have to do with us, right? So how can we use the Fourier transform to characterize what we care about, which was the translation equivariant structure of the grid? So remember that's what we are looking for, right? We wanted to characterize the matrices that commute with shift. And now we have just found the eigenstructure of S. So let me ask to the group here, how do you connect the dots? I mean, what is the relationship with the eigenstructure and this commutativity property? Someone wants to answer? And I don't see the chat, so maybe if you want to answer, just unmute yourself. No? Okay. So the fact, I mean, this is a simple fact, right? Is that two matrices commute even only if they share the same eigenstructure, right? And so what this means for us is that we can understand linear equivariant operators in a way that in terms of their Fourier eigenstructure, right? So these are all the matrices that can be diagonalized also in the Fourier domain, right? Because this is the basis that diagonalizes the shift. So these are matrices that can be written as the Fourier transform times a diagonal matrix times the inverse Fourier transform, okay, for certain vector of coefficients. So what do these matrices look like? Okay, so let's here's a simple simple chains of identities, right? So let's try to go together, right? So we have this matrix applied to a vector x. I can by first using the inverse Fourier transform, right? I can express x as the combination of frequencies, right, with the inverse Fourier transform. Then I can query, I can use the fact that C is linear, right? Because it's that's my assumption to put the C inside. And now I can use the assumption, the structural assumption that C is diagonal in Fourier, right? So I know that this guy is an eigenvector of this guy with a certain eigenvalue. Okay, so I have this important identity here. And now I can look at what happens in coordinates, right? So I can look at now the coordinates of this scheme. So in coordinates, right, I can now evaluate this vector at coordinate j. And so again, I can obtain a very nice characterization. And the main tools, I mean, here I'm putting here on the right hand side the tool that is behind every inequality, right? But as you can see, this is really showing you like a tiny fraction of the power of Fourier transforms, right? I mean, all these identities are direct consequences of the definition of Fourier transforms, right? So in particular, the first one here is that I identify this sum here as a dot product between two Fourier transforms, the Fourier transform of alpha, right, which is what I have here, and then the Fourier transform of something that looks like the Fourier transform of x, but not quite. It's the Fourier transform of a shifted and inverted signal. It's like the Fourier transform of, like the conjugate of the Fourier transform is the Fourier transform of the shifted signal. And so here, what you can see by applying Parseval is that you can re-express this dot product in space again, and you get to something that is quite familiar. Okay, so here I know that the convolution, this C of x evaluated at j, looks like a sum over all the indices of some translated version of x times the coefficients of the filter. So here we are just rediscovering convolutions, right? So this is almost like this is the definition of a convolution operator. Okay, so what we have just seen is that if I start from the assumption, the hypothesis that my matrix, my linear operator commutes with shifts, then I arrive at convolutions. Obviously, this implication is very easy to go in the other direction, okay? Because if I have a convolution, right, a convolution, I can re-express it very naturally as a linear combination of shifts, right? That's the definition of a convolution. And so, you know, if you want, you can see this as a polynomial in the shift. So of course, if now I apply a shift into the left or to the right, I get the same thing, right? Because a polynomial commutes with the polynomials, they commute. Okay, and this is again something that if you want to formalize, you can try to formalize it yourself. Okay, so we have seen that we have essentially finished our exercise, right? So we have seen that all the linear operators that are equivariant, that commute with shifts, are precisely convolutions, and these convolutions are can be very naturally expressed in Fourier as being diagonal, right? This is this very nice commutating, this very nice diagram that gives you the full correspondence. And of course, the locality of the model, the locality that we see that is important in the blueprint, is just expressed in the fact that this filter, this spatial filter, is only going to be non-zero for certain locations, right, that are in general much smaller than the domain. Okay, any questions that so far? I see that people are quite silent. Okay, let me continue. Okay, so let me present with you a special case. So let's assume that I have spectral filters that are the opposite of being local in space, that are very local in Fourier. Okay, so this is like a spectral multiplier that is only it's only non-zero in a single frequency, and in the rest is completely out, right? In the rest is completely zero. So what does the blueprint become if I make this choice of equivariant operators? Okay, so I compute these equivariant filters, but every one of these equivariant convolution is a pure frequency. So in that case, you can verify that the blueprint, in fact, just stops after one step, right? Because after I apply this very particular convolution, my signal is no longer varying in space, right? It's completely delocalized in space. So in particular, I can consider one instance of this model where I take as an activation function the modulus. Okay, so I consider a representation of X that is just taking the Fourier transform and killing the phase, right? Just keeping the modulus. So the question is this representation translation invariant? And I wish I could see the chat, but I don't see the chat. So if someone wants to unmute and answer. No. Okay.
Okay. Is anyone having an answer? Just unmute yourself and speak.
Okay. Anyway, so I'll try to answer. I try to infer. So is the representation translation invariant? So the answer is yes, because if I look at as I said, if one of the properties of translation, so if I translate the signal in Fourier, this translation is expressed, as we saw, as just a multiplier, right? Like it's, as we said before, translation is diagonalized in Fourier. So the only effect of translating is changing the phase, right? Remember the eigenvalue that we discovered before when we were applying the shift was a complex number of modulus 1, right? It was a pure, like it was a unitary complex number. So if I take the absolute value, this eigenvalue is killed, and so I get exactly the same output as before, right? So that's what you see in this equation. But there's a problem, right? So there's a certain problem that this kind of representation is hinting at, right? There's a bunch of important problems. The first one is that the Fourier invariants lose information, right? And here I just try to illustrate what happens, right? So here I have two pictures of two very famous scientists. If I apply this Fourier transform, right, in the Fourier domain, coefficients, they have two components, right? The modulus, which is the one that we are keeping here to get the invariant, and the phase, right, which is the phase of these complex numbers. So what happens if now I swap the phases of these two guys, right? So I keep the modulus, right, and I just perturb the phase, and then I invert. What you see is that if I apply this phase swap here, what you get if you transform Newton, you get basically something that looks much closer to Fourier than to Newton, and vice versa. So the way to interpret this is that when most of the information, right, the semantic information is carried in the phase, right, not in the modulus. Okay, so if I throw the phase, right, the representations that throw the phase, they are very lossy, right? So in that sense, I was too greedy, right? So this blueprint that tries to directly use the spectral property of the group and just use the eigenvectors of the group to create invariants, it goes too quickly because it throws too much information. There's another issue that is even more important, that is some form of brittleness of this Fourier representation. Okay, and for this we need to think a little bit out of the box. So far we have been just focused on a very tiny translation symmetry structure, which is just the translation group. The question what you should ask is what happens outside the translation group, and what does it mean outside the translation group? So here let's assume, again for simplicity, that we are in a continuous domain now, so I can define this thing outside in an easier way. And so the translation group, we can think it as a subgroup of a much larger group of translations, right? So any change of any transformation in the domain that is not necessarily moving every coordinate by a fixed vector, right? So in particular, I can think about any transformation that goes from the domain that is invertible and leaves the domain, goes from the domain to the domain. And this is, technically speaking, is called the group of automorphisms of the domain. And think about this here more illustrative purposes, think it in this sense, right? So if I'm in the full group of all possible transformations of the domain, I can just consider very simple, very small number of transformations that are shifts, that are rigid shifts. But this lives in a much, I can do many other things. I can take the image, I can take the pixels and move them in a way that they are non-rigid, right? I can create a distortion. And so there's something important, which is how close any diffeomorphism is to the symmetry group. Okay, so you can measure how close this distortion, the amount of distortion. For example, you can measure it by how much the domain is being stretched. And you can measure this, so because the way you interpret this measure of smoothness is like as a distance to the translation group. In particular, we have that the transformations that happen to be in the translation group, they have perfect smoothness, right? Like the distance to the symmetry group is 0. And here I try to illustrate, right? So as you get farther and farther and farther for the translation group, you can accomplish more and more complicated distortions of the domain. Okay, so, and here, this is just like a natural extension of the invariance prior, that instead of asking the target function to be just invariant to the action of the group, now we ask it to be stable to deformations, right? So everything that goes outside this group, I also want to have some certain control. And in particular, you can verify from this property here that this condition includes the invariance property that we had before. Okay. And so why is deformation, sorry, and why is the deformation stability a useful prior? Well, you can see that in many areas, again, of engineering and science, this is a very powerful prior. Okay, in the sense that there's these kind of transformations, they appear very naturally in many areas, of course, in computer vision, right, in recognizing objects in a scene, also in computational chemistry and physics, like there's a molecules can be deformed and they preserved most of their chemical properties. And of course, as you can imagine, when we try to do like geometry processing in graphics, the deformation, non-rigid deformation, are like the bread and butter of these domains. And we are going to see Michael's lecture, in the manifold lecture, we are going to see how deformation is also like an important, kind of a crucial aspect to consider in the context of the blueprint there. Okay, so are these Fourier invariants, are they considered to be, can we show that this thing, if this representation based just on the Fourier, whether it's deformation stable or not? And so this is a little bit of like a technical step, and you can you know, if you don't feel, if you can feel free to just skip that if you don't feel comfortable. But the key is that here in this example, we can show very easily with this example that this representation is not going to have stability. Okay, and so to do that, we have like a small window, like a window. This is an example in 1D that considers like a low-pass window with a certain bandwidth. And then this is what's called a modulation, right? You take a signal that you take this low-pass window and you multiply it with an oscillating wave. And then you take this function and you try to deform it by slightly stretching the domain, right? So this is a diffeomorphism that has a certain amount of elasticity, right? So here it's not a pure translation. So what you can, if you look at the effect of this deformation in the Fourier domain, right? And this is this picture that is expressed here, you can see that as long as there's a certain separation, right, between the central frequencies, like the effect of this deformation is going to do two things. It's going to move the central frequency of this function, right, from psi, that is here, to 1 plus s times psi. And then it's also going to spread a little bit the bandwidth. But the effect in the bandwidth is different from the effect of the central frequency. So in one case, it's additive, and the other case is multiplicative, which means that as soon as the central frequency is sufficiently large, even if s is very, very small, we are going to see that this representation does not satisfy the stability. Okay, and for more details, of course, you can feel free to go to reach out to me offline or to look at the related references. But the key point here, like the takeaway, is that this representation that is only based on the spectral properties of the domain is unstable. Okay, so and the main problem here are the high frequencies, right? So we saw before that the eigenstructure of the translation group is consisting in Fourier atoms. So any Fourier atom, independently of the frequency, is an eigenvector. But as soon as I'm not considering a translation, but a tiny something that deviates a little bit from a translation, this eigenvector is no longer useful. It's completely unstable. So what is the solution to overcome this instability. So the solution is really to move away from looking at things at the Fourier domain and trying to take a different angle, a different perspective. And this is really this perspective of multiscale representations. So multiscale representations, in a nutshell, what they try to do is, instead of extracting information at every frequency, right? So this is this example. If I take an image, if I express this image in the Fourier domain, you will see something that is quite very hard to interpret, right? So here, there's every point here corresponds to a different frequency. So instead of representing the information in terms of frequency, we represent it in terms of scales. Okay, so in terms of scales, as we described in the previous lecture, the idea is to think about this image as containing details at different scales, right? So this here corresponds to the details at the largest scale. Here we have, so at the finest resolution, we add details at the coarser resolution, and so on and so on and so on. And so how can we do that in practice? So in practice, we can do it with what we call a wavelet convolutional filter bank. Okay, so a wavelet convolutional filter bank is just a collection of convolutions that are where the filters, here this is a filter, psi alpha. And so this phi alpha, these filters are all generated from a single mother wavelet, if you want, right? So there's a single filter psi. Well, you can think about this little filter psi as a wave that oscillates, right? So it's a wave that is localized in space, right? So if you in 2D, think about this little guy here, right? It's a little function that oscillates. And then once I have one of these waves, I can generate the whole family. How can I generate the whole family? I can generate it by dilating it, right? Shrinking it and making it bigger and smaller, and then also rotating it in space. Okay, so I can create like a full family of filters from a single one. So these filters taken together, they define a linear representation, right? A linear transform that is actually very well behaved. It's very, very well conditioned, right? If this is something, if I design the wavelets appropriately, I can do that. That's what's called in harmonic analysis a Littlewood-Bailey transform. But for us, the key aspect here is that this operator, right, because it's a convolution operator, as we saw before, it's equivariant to translations. But it's not only equivariant to translations, it's also equivariant with deformation stability, in the sense that if I think about the commutation, right, if I try to commute a deformation with a wavelet, I get an error that is only depends on the elasticity, right? I remember before that this property is not true for arbitrary convolutional operators, right? So this property requires the multiscale structure. Again, the details of this result are pretty technical, and I will refer you to some of the references if you're interested to know more. But the point here that I want to make is that now we can look at this wavelet filter bank and plug it directly to our blueprint. So bypassing completely this learning aspect. So how can we do that? And this is the content. This is the essence of the wavelet scattering representation that was introduced by Stéphane Malat a few years ago, and also by myself. Okay, and so how can we combine these three building blocks of the blueprint? So what we have is we start from a local linear invariant. So this we know how to do. We are just defining a local average, right? A local filter on the image. We are going to complement this low-pass filter with a filter bank that is equivariant and stable. This is this wavelet filter bank that we just described. And the third ingredient that we need in the blueprint is an element-wise activation function rho. Okay? And so the first thing that we can do is to start with the simplest of these ingredients, which is the linear, like the low-pass filter, right? So if I take the image, I can apply this low-pass filter, right? I can do it at different scales, right? I can end up with this object here. That's this coordinate here. Of course, as we know, this representation is not ideal, right? Because as we know, this operation loses a lot of information, right? All the high frequency, all the details of the image are lost. Okay, so how can we recover this information that is lost? Well, we recover it with our wavelet filter bank. right? So we can recover it with the filter bank. Okay, so we apply it here. This filter bank, right? As we saw from the blueprint, we need to pass it through a nonlinearity in order to extract new information, new invariants, right? So we apply this activation function, and then we apply the low-pass filter again, which is our way to generate invariants, right? That's what's done here, right? So we complement the low-pass filter with new details, and then we propagate them back, right, to get these low-pass coefficients. Because we have applied this low-pass filter again, we have lost information. So we can do it again, right? We can recover the complement that this guy has lost. We can apply again, or high-pass filter, or bandpass filters. Okay, and then we can propagate them back using this this low-pass filter. Okay, so this defines a scattering transform, which is just a very if you want, like a bare bones version of the blueprint that completely hardwires the choice of equivariant filters. So because it has such a like we have such a control over the filters, there's a bunch of interesting mathematical properties that one can prove. In particular, we can show that because this representation is built from operators that have where we have a good control of how much energy they lose, like in terms of L2, the total energy can also be shown to be preserved. And also, more importantly for us, because we are building this representation, this blueprint from operators that are designed to be stable to deformations, the overall representation is also stable to deformations. Okay. So this is really like in stark contrast with the Fourier modulus that we saw before, right? We saw before that the Fourier modulus, if we put it here, that was actually of the order of the norm of x, right? It's not small when the deformation is close to translation. Okay, so that's one of the key differences here. So how can we actually use or understand leverage scattering representations in practice? So there's a bunch of interesting properties or benefits of a representation that doesn't require much learning. So in particular, it can be used in different areas of physics to define fields like statistical models for complicated physical phenomena. So here I'm showing you different flavors of that. So here's an example of a turbulent flow. That's something that is studied, that is very important, for example, in climate modeling. Here is an example of an icing model. This is like an example of a glassy system, very important to study criticality and glass. And here is an example of weak lens cosmology, right? So these are like, data that you can get from physical world. And so building statistical models is important. And here we have here I'm giving you samples from the generative model based on this scattering transform. Again, here there's no training inside, right? There's no like complicated algorithm to adjust like a GAN or whatever, right? This is just using a scattering transform to define a very simple statistical model. It can also be used in cosmology to infer certain cosmological parameters. And as you can see here, it's in some of these applications, you get basically the same benefit as the more complicated CNN, with the benefit that there's no training, right? Everything can be completely interpreted. And of course, this thing can also be used in quantum chemistry with some of my colleagues. Of course, you can also use it for computer vision, for classification, by using, again, this very simple blueprint here that is purely based on wavelet, followed by a linear classifier. And if you do that, you get some results that are decent, that are okay, that are good for MNIST. They are kind of decent for CIFAR, but they start to be like pretty bad, right? The errors here start to be pretty bad for as long as the problem becomes quite complicated. So the question you might ask is, okay, what I mean, clearly there has to be like a downside for giving up so much power, right? So here we are not learning anything in this blueprint, right? We are just producing features, right? And then they're assigned to some linear classifier. So the thing that is missing, right? The important part that is missing is that this blueprint does not try to address the interactions between feature maps. And so this is really how one should try to understand like the final contribution, the final push that convolutional neural networks are able to do relative to these like principled multiscale representations. And so here, just to give you like the punchline, right, is that by taking what we had before, like these wavelet filters, if we concatenate, if we interleave from one layer to the next a set of coefficients, right here, a trainable coefficient that is just trying to address the connection across the different wavelet channels, right? So here we interleave at every time that we go from one scale to the next, we apply a one-by-one convolution. Okay, this is like a one-by-one convolution. So if you do that, then the kind of the gaps with respect to the deep network is essentially closed, right? And here there's of course one word of caution is that the deep networks always also keep improving, right? So this comparison is using ResNets, and this is let me just mention that this is the work of Joan and people from the École Normale, led by Stéphane. And here also like some previous work along these lines by Edouard Oyalon and colleagues. Okay, so as I said, modern neural networks, convolutional neural networks, they have many tricks, many heuristics that make that things keep improving, right? So here, the comparison that I was making was with the ResNet model that is like this point here, right? So ever since the neural networks, they keep adding things and things and things, right? That make their efficiency even better, right? And for example, they include these like residual layers, these dense layers, normalization layers, and so there's many of these elements that are not explicit in our blueprint. They're essentially still a mathematical mystery. For example, we still don't have a good understanding of how to describe like the space of functions that are associated with a certain CNN that maybe can help us understand what is the role of the depth beyond the scale, as I showed you before for wavelets, or what is the role of the width of the filter. And many of these questions are complicated precisely because they blend together, they're intertwined together, aspects about architecture like approximation, that's the focus of our course here, with the aspects of optimization, right? As soon as one starts to try to make these architectures trainable, of course, one needs to many of these choices, they are not independent, right? Like the choice for architecture and the choice for optimization are very close to each other. So just as a takeaway, like trying to close it, and so that we'll have hopefully time for a few questions. What I try to present you here is that the grid offers us a very nice playground to understand and to build theories, because the grid is a very rich object, right? That has a lot of analytic structure, geometric structure, algebraic structure, and we can really use it to push quite far our understanding of the blueprint. Like, why are we making these choices about different scales? Why the linear structure, equivariant structure, is sufficient? And an important element that is very that we use, that the grid allows us to say things about, is this role of the deformations, right? If one just tries to build axiomatic representations just from the notion of symmetry and invariance, what I showed here is that this view is not sufficient, right? It misses the point. So wavelet scattering is an instance of the blueprint that kind of throws away most of the training. It just puts all the training at the last layer, and it's something that one can also use to understand again some of the theoretical underpinnings of the blueprint. But of course, this wavelet scattering is not nearly as powerful as CNNs. So CNNs, really, I view them as a culmination. It's almost like the perfect algorithm, right? So it's a perfect algorithm. It's a perfect architecture that really has the right balance between all the geometric bias as well as the representational power. Again, there's many things that are still open in terms of understanding. And so in the next lectures, we are essentially going to move beyond the grid world and see how this blueprint can be instantiated beyond this domain, right? In particular, Taco is going to tell you about how this blueprint is instantiated in groups, and Michael is going to describe how to do it on manifold and meshes. So with that, I'll thank you very much, and I'm open for questions for in the minutes that we have remaining.
Okay, thank you very much, Joan, for the lecture. So if anyone has a question, you can unmute yourself. In the meantime, I would like to ask about the wavelet. Is it like a modification of the Fourier, Fourier to kind of integrate scales, the scale deformation stability?
Yes. So you can really think it's a good intuition. So you can think about Fourier transform as a transformation that is going to try to isolate the content of the image at every frequency, right? It's going to try and then process every frequency separately. What the wavelet transform tries to do is, instead of treating every frequency separately, it treats information by groups, by packets, right? And the reason for that is that you cannot treat high frequencies separately, right? You need to process them together. And the way to process them together is by extracting like filters that have some spatial localization. And here, of course, it's very hard to do like a course of harmonic analysis in 30 minutes, but the thing that is behind this trade-off is what's called like this Heisenberg uncertainty principle, right? Is that if one wants to extract information that is so like the way to extract information with a filter, it always involves a trade-off between how much localization I want to have in space versus how much localization I want to have in frequency. And so you cannot have both, right? You cannot have a perfect localization in both space and frequency. So wavelets, you can think about this as a particular trade-off where the trade-off is really driven by the notion of scale, right? So like the wavelets, as you saw in the picture here, maybe this is a good picture, right? So this picture here, right, as I take the wavelet and I shrink it, the effect of shrinking the wavelet in space is the opposite effect in Fourier, right? So it defines a kind of a tiling of the time frequency axis that is specific to this problem, and it just happens to be the right trade-off to have the stability to deformations.
I have a question here related to wavelet. Understand wavelet is stable
Yes.
when I have signal deformation.
Yes.
Okay, if I have also domain deformation, is it stable also?
Yeah, that's a good question. So here we really focused on signal deformation in this result. If you have domain deformation, we are going to see, actually, Michael is going to show you what happens in that case. But the punchline is that the conclusion is essentially the same, right? So like domain deformations can be can also be stabilized by a representation that is essentially multiscale, right? So like the eigenfunctions of the, like you can take the domain and you can look at the spectral properties of the domain, and when you apply a deformation in the domain, there's some aspects of this spectrum that are stable, that are preserved, and in order to get the stability, you need to group the eigenfunctions together, and you need to group them precisely the way wavelet groups these things, right? So like the more high frequency you go, the more you need to do the grouping. But I think that, yeah, Michael is in the lecture, I think it's, I don't know, maybe 9. You're gonna get some of these, right? You're gonna get we're gonna describe what happens in the case of domain deformation.
Okay. Another question also about method in CNN. You mentioned something about residual connection and batch normalization.
Yes.
Is this illustrated in geometric blueprint?
No, so that's the point. So the blueprint is trying to stay a little bit high level. So it doesn't really prescribe how exactly to parameterize the linear structure of these equivariants, right? So residual connections, of course, one can define them in a way that they preserve all the kind of axioms of the blueprint, right? In the sense that that you have like a residual connections that are equivariant to translations, but their effect, their effect is really in combination with optimization, right? So in other words, if you want to understand the benefit of normalization and residual connections, one needs to look at the problem in more globality, right? It's not just in terms of finding a good representation, but it's also like the question of how to optimize it, right? What is the algorithm that you use to train these networks? So these are still like I would say important open questions to really understand better the interplay between these choices and the training.
Okay, thank you.
Okay.
Yeah, there's another question from here.
Good morning.
Yeah.
Please, you say that the Fourier transformation is unstable. So,
Yes.
but I want to relate that one in physics, because when in physics you have a signal, and when you deform the signal, you cannot, I mean, directly conclude that the signal will be stable or unstable. You have to look for the area where you get the stability and the area where you will not get you have instability. So I don't know why here you directly conclude that in the case of the Fourier transformation for this kind of signal, you have just instability. So I don't know if you can comment more about that one.
Yeah, so I mean that's a good point. So what it did is to illustrate that if one just sticks with Fourier, so if one wants to just use Fourier all the way till the end to get like a kind of a nonlinear invariant representation, one is confronted with the fact that high frequencies, right? If you look at the high frequency of the signal, these high frequencies are unstable to deformations. And here, when I say deformations, I mean something very specific, right? I have a signal that is defined over some, let's say, continuous domain, like in 1D if you want. And then I apply a deformation, which is just a warping, right? I apply a warping of the domain. In the example that I showed, it's just a dilation, right? I just do like a slight dilation of the domain. And so at the end, the reason why this example works, it's not very surprising, is that if I think about the information content in terms of frequency, and I apply a dilation, you know that the central frequency, right, is going to scale, is going to move by a factor that is multiplicative in frequency, right? So like if I have a frequency allocation, let's say xi, and I apply a dilation, the new information is at location xi times the dilation, right? So the difference in, you know, like the frequency, like the information has moved. The more high frequency I have, the more I have something that moves. So if I want to have something that is stable to deformations, I need to process these frequencies together, right? Because if I do it individually, I'm going to see that it's basically just, it's the same reason why if I have an image, right? And I just look at the L2 distance between an image and a translated version of the image. So this distance is unstable to shifts, right? Because if I have something that is high frequency and I translate it, I can be very far in L2. Yeah, you think about the example of a little, let's say, a little spike, right? If I have a spike and then I just translate it, I get a spike that is in a different location. So it's very far in L2. So the reason why in this example that I showed is essentially the same reason, right? Is that if I have deformations, they have the same effect in the frequency domain as essentially translations in the spatial domain. So you need to have somehow like something that is in between the space and the frequency, and that's precisely the wavelet representation, right? That's precisely the multiscale representation. I hope that this was slightly clarifying.
Okay, I get. But I don't know. I have a following question about that one. So you said that in the case of the scale representation, because if I remember very well the scale representation,
Yeah.
in the scale representation we use two kind of deformation. If I remember very well, we deform the space and we deform the time. And when you deform the space and the time, after you can maybe try to get some information about that one, like maybe you can decide to work on this time or you work on the space. So by working on the time, you can decide to get some order of representation. So is this the one that you are doing here?
Yeah, so here what I illustrated is the scattering representation on just the pure like translation group. So it's really, you should really think that you have space, right? Like think of it as a transformation for images. So there's no time, right? So think about like a 2D, and then you apply, the object, like the variability, like the kind of the images are subject to deformations. And how do you define a deformation here? It's just like a warping on the image plane, right? So you, like the example I show you with a person that has kind of like the head that was kind of tilting, right? So these are the kind of the transformations that we want to build stability against. And there's something that I didn't say, but I think it was present in the slide, that I think is an important point, is that when it comes to deformations, we are interested in stability, not invariance. Okay, and I hope that this is clear for everyone, that we do not want to have invariance to deformations, because then it would mean that the representation doesn't see that this video is moving, right? It's like it would give you the same representation at every frame. We don't want that, right? We want to be able to still separate, identify, discriminate the different content.
Okay, thank you.
Yeah. Okay, any more questions?
Any more questions? I think we are over time. So
okay, so I will upload you the PDF of the slides today, and I'll be keeping an eye on Campus Wire this evening.
yeah,
okay.
Yeah, I'll also record put the recording up so people are able to go through again and try to consume it a bit more. Yeah, so you pass our questions on Campus Wire then.
Perfect. Bye everyone.
So